to just summarize the process of how do we build an optimal controller. And I'm going to do this for a linear time invariant continuous time system, and where A is an m by m matrix. And I'm going to do this slightly in a flowchart kind of form-ish to kind of talk about it and how we build up to finally getting a full system, something that looks like what we're seeing over here. So now we look at this and you say, all right, we start out with the system, we go, well, is A unstable? Is the system unstable? Or is it not like stable enough, right? That's where the first question. This is an eigenvalue question, and you're going to look at the eigenvalues and go, okay, what do I do with this? One of the other questions is like, well, if it's not, then I probably want to talk about building a control system. Well, what am I going to do first? Well, I'm going to first say, well, can I control the system if I had x? So if I have all the values in x, right? So if I just have this top equation, I have all the values in x, so I know what all the state variables are. Could I control the system? Well, the question is going to be basically going, for example, asking what is my controllability matrix? And is it of rank m? Remember I told you A is an m by m matrix. Is this of rank m? Okay. If it is, cool, we proceed. If it isn't, then I got to ask questions. And there's different issues on the rank. You know, is there an issue with B? Because B is my way to get into it from U. That could be one issue. Could be, is A just actually, not of a full rank itself? It's a fair question, because you might just go, you know what, maybe I thought the system was a fourth order system and it's really third order. That's good to know, and that's good to kind of build into the formulation right from the beginning. Multiple things like that are relevant. But let's say the answer to that is yes. Well, then I could say, all right, let me use LQR, so the linear quadratic regulator, and I would find there's sort of a key parameter here, k sub r. K sub r is basically going to be the parameter of how much does the u feed into, or how much does the x then feed into the u. And that works really well, again, assuming we know them all. We can do this optimally, and there's an optimization for this. Okay. Now I get to talk about two matrices, Q and R. These are actuated, kind of gives you a ratio of what the cost is of actuators to sensors. Sensing basically, it's like, okay, how well can I get the states versus how well can I actually actuate the U of t part? And you kind of can talk about the optimization, and there's different ways to play with this. When you do this, and you do this optimization and this constrained optimization, what you find is that you basically get a Riccati equation solution, which is a quadratic equation. One of the two equations are stable. You may call it an algebraic Riccati equation, because technically there's a differential equation form for those who are curious. But this is usually the form, and this kind of a form of Riccati equation for the second equation. Once I get this P matrix is symmetric, then I basically can find K sub R by knowing what this R was originally in the matrix, B and P. Notice how important B is here again. It shows up again in terms of what you can do for K sub R. Okay, really important there. If you're someone using MATLAB, there's actually commands for this. I'm pretty sure there's probably something in Python and any other equivalently kind of structured languages, because it's just too important of a thing in terms of how these are all put together. Cool. So once you have that, then you say, great, but the problem is I really probably don't have x. I really have y, and in general, y is a smaller dimension than x. So can I get to y? And that's really going to depend on what is C, and it's going to depend on the structure between A and C. The first question is, and I'll talk about this as of an observability matrix, and I want to know what is its rank. And if its rank is of M, then I'm like, I can see everything. It gives me the dimensions to which I can see it. Now I will care both in the controllability matrix and the observability matrix how much the spread is in the eigenvalues, because the eigenvalues are also going to say how much energy do I have along a particular direction or in an orthogonal direction. And if those eigenvalues are widely spaced, well, one direction I can control really well, but the other one maybe not so much, and that might actually get within the limits of the range of which I can get hold of. And so I really need to realize that it needs to be relatively solid and robust in those cases. You might even ask, well, what happens if it says no? Well, probably what happened is I chose the wrong sensors. Because usually y is smaller than x because I only want to make so many sensors and it's a convenient place and I'm going to put it there. Well, it turns out that that might not have been a good idea. That's usually one of the first things that comes into play, and you're like, hey, maybe I need a different sensor abilities, and try to see if I can make it work. Okay. But assuming that it does work, yay, then I can find K sub f, which is a term in sort of the optimization term in sort of making a filter that's supposed to look like this filter, that I'm trying to take the U and the Y terms and knowing the A, B, and C matrices and kind of estimate X, right? And so I have an additional term into there to kind of force the error, to force them to be close. We'll often talk about these things as Kalman filters, or they get talked about that way, or other general estimation filters. Cool things to look at there. Now, you can optimize for this as well, and here you actually optimize based on the covariance matrices of the disturbances and the noise to the best that you can get those values. And then your error metric that you're going to optimize over deals with an expected value of that, grading those values. It turns out the good part about it is you get another algebraic Riccati equation that is very straightforward, just using these two matrices, and you can actually then talk about what your coefficients would be that kind of helps force things together in an optimal way. In other words, making sure that the actual output and what we'll often talk about is the error of the signal, the error of the estimation, to get as close as possible. And here there's also a MATLAB command, Python command, and so forth to do all this. Now there's an additional step that you'll always ask, is like, is this a robust system? And that's going to get you into loop gain sensitivity and co-sensitivity questions and to try to see where that plays. But if that's the case, then I can actually say that I built my system. Here's the original system, which would have this elements, but I'm also going to have my disturbances and noise in there, and I have to deal with that. I may, in fact, also have an additional input into here, but just keeping this part straightforward. There's going to be the LQR system, but now it's going to be over the estimate of X. And then I'm also then going to have my filter here for LQE, which is going to obviously have some effect of U and some effect of Y, but of course it also has some noise in it, yay. And that's what we get to calculate out. And what's nice is then if you look at this in an X, X for your X variables, you get this sort of X and E. E now is really the error, the difference between X and the X estimate. And what you can find is then you can write this as really one set of state equations. Very nice that these two aspects, these are the things that come out of LQR and LQE, actually sit on diagonal so the eigenvalues can be separated a bit. And this works out well, so you can look at them separately as the idea. And this often works out well within this kind of a formulation. And then, of course, you have the effects due to disturbances. But then this gives you the overall system. This is the flow of which you would approach. Obviously, there's some tweaks in it depending on who's doing what, but this is the overall flow, and trying to put it in one place so you can see where everything happens at the same time.